Hello. Okay. Hi, everyone. Thanks for coming out for my talk here today. So for those of you who don't know, which is most of you, I assume, I'm Travis. I work on the machine learning platform here at Uber, also known as Michelangelo. I work up in Seattle on the deep learning infrastructure team, and one of the things that we do up there is develop Horovod. So Horovod, as you'll come to know, is our distributed deep learning training platform. And the value proposition that we like to give for it is that you can train your models with scaling up to hundreds of GPUs with just 5 lines of Python in your existing training script. So in this talk, we'll give you a brief introduction to, and by we I mean me, I'll give you a brief introduction to what Horovod is, how you can use it in your existing scripts to scale things up. And for those of you who might be already familiar with Horovod to some degree, I'll also talk a bit about some of the things that we're doing to improve the system and make it even more awesome for your use cases. I have my speaking notes on my phone, so I'm gonna probably get out of sync at some point, but we'll try to get through it. Okay, so the first question that I want to address, so I'm sure all of you are naturally familiar with deep learning. It's kind of like eating the world these days, but I think it's important to talk a bit about why exactly deep learning is becoming such a big thing now. And the answer to this question, as Andrew Ng's graph here so eloquently puts it, is that what we're seeing is that we're having a lot more data at our disposal today. And as it turns out, we have this diminishing return effect that we've seen in a lot of traditional machine learning models that we're not seeing to such a degree with deep learning just yet. And so as we continue to get more data in our environments at our disposal, at our fingertips, we're able to get a lot higher performance, where performance here we mean the model performance, the quality of the model. And on the other side, we also have now these great frameworks like PyTorch, Keras, TensorFlow that are making these sorts of performance benefits more accessible to people who might not be specialists in certain areas. And so this confluence of these effects is what's kind of driving companies like us here at Uber to start taking advantage of deep learning. So in the past, what we saw was that deep learning was mostly something that research groups within Uber primarily focused on, but now that's no longer the case. Now we're starting to see more machine learning practitioners that have a background in using Spark workflows and using MLlib, things like that, starting to use deep learning in production. And that's ranging from all sorts of use cases from self-driving vehicles obviously is one that I'm sure a lot of people are familiar with, but as the Pyro folks mentioned, trip forecasting as well, fraud detection, pretty much any problem you can think of. Okay, so deep learning, what makes it different from traditional machine learning? Why can't we just use commodity hardware like we did in the past, like Hadoop or Spark, to solve this problem right out of the box? And that kind of comes down to the fact that deep learning is called deep learning because it has so many layers. The models are so complex that we end up needing specialized hardware like GPUs in order to run this in any tractable amount of time. And similarly, what we see is that the gradients are computed sequentially backwards in these models with very limited opportunities for parallelism. And so systems like Spark that assume embarrassingly parallel computation also have difficulty scaling to the requirements of deep learning. So as we start thinking about how we go about distributing this workload, we have kind of like 2 separate paths that we can explore, model parallelism and data parallelism. So in the model parallelism viewpoint, it's limited in the sense that you scale to the degree that your model is innately parallel. So in the previous slide, we saw that there were some layers that could be computed in parallel. They were independent of one another. So those are opportunities for model parallelism. But with data parallelism, it's more generally applicable in the sense that regardless of your model structure, if you have a lot of data, you can scale it out. But it does add the additional complexity of needing to synchronize state across multiple individual workers. So what we observe as we talk about at the beginning was that we're getting a lot more data. A lot more data means a lot more complex models, but that's a double-edged sword in the sense that more data means slower training when you're holding constant the number of compute resources you have available to you. But what we also know is that modern GPUs have a lot of RAM, and that most models that we use today, despite being very complex, can still fit within a single server. And so the solution that we have that we want to explore in order to speed things up is going to be to spread out the data, because data is fundamentally the bottleneck in the training process. So one of the first techniques that people implemented in order to scale out with data parallelism was this idea of parameter servers, still around today. And the idea is essentially that you have a sort of single source of truth for your model's parameters. So on the left, we see you have this parameter server, contains the truth. All the workers working on some subset of the data report into the parameter servers their changes, and they get back the most updated parameters from the server. So that works pretty well in practice, but of course you can imagine that the parameter server can become a natural bottleneck. And so what you can also do is on the right there, you have multiple parameter servers. Every server is independently responsible for some subset of the gradients. And then the workers communicate with those parameter servers together. And that adds a lot of additional communication complexity, but it's a good way to avoid some of these bottlenecks. But when we start thinking about how we want to build a deep learning, distributed deep learning system for Uber's needs, one of the things we noticed with parameter servers that was a bit of a challenge was that parameter servers, at least as TensorFlow provided them kind of out of the box, require a lot of coupling of your model training script with the actual infrastructure of distributing your network, or distributing your training. So you have the engineers adding a lot of code in there to set up these parameter servers and to define how they're going to be used. And what we wanted to do was make distributed training both fast in the sense that it scales really well. You add more GPUs, you add more nodes to the cluster. Your training gets faster without a lot of diminishing returns. But we also wanted to make it easy in the sense that we have this separation of concerns where the infrastructure engineers, like us on the machine learning platform side, can be responsible for setting up the environment, the servers, the networking, building the containers, deciding what hardware to use. But then the machine learning engineers who are building these models can focus specifically on their problem without having to think about how am I going to distribute this? How am I going to scale it? And that's where Horovod comes in. So Horovod is this distributed deep learning training system for TensorFlow, Keras, and PyTorch with MXNet coming down the pipeline soon. And it achieves this goal of separating the infra from the ML. And we make it really easy to use. You already have your TensorFlow or PyTorch installation on your machine, and you just run pip install Horovod, and suddenly you have access to this framework. And it makes use of bandwidth optimal protocols that you might have in your environment. So if you can use remote direct memory access, Horovod can take advantage of that, InfiniBand. And our project lead, Alex Sergeev, came up with the name Horovod. It's named after a traditional Russian dance where the participants dance in a circle with linked hands, which kind of nicely segues into the explanation for how Horovod actually works under the hood. So Horovod uses, as its algorithm, what we call, or what is known as Ring-Allreduce, where the gradients are averaged after each step synchronously in this kind of circle of passing bits of the gradient from one worker in the chain to the next. So there was a paper published, I believe it's listed there, aptly named Bandwidth Optimal Allreduce Algorithms for Clusters, such and such. That demonstrates that this is actually the bandwidth optimal algorithm for this task. And what you'll see is that at each step, the workers communicate with two adjacent workers. So one of the workers sends updates to the node, and then that node passes updates onto the next node. And so what you end up with is number of steps in proportion to the number of workers, which works out nicely to avoid this sort of end-to-end communication bottleneck that you would think might arise in like a naive kind of decentralized approach to this problem. And how does it do in practice? It does pretty well for us. So what we found is that if you look at the sort of rectangular bar as being the one-to-one kind of linear scaling, like optimal effect of like adding more GPUs and getting more inputs per second in terms of performance, we see that Horovod scales to about 90% of that ideal in most cases for most networks. And even in the case of VGG 16, so a network that has a very dense network, it still scales pretty well, particularly in the case where you have RDMA available. And ends up scaling well past 128 GPUs as we see there. So if that has managed to convince you that Horovod performs pretty well, and you're now interested in using it in practice, let's go ahead and quickly dive into how you can do that. So as promised, the title of this talk, 5 Easy Lines of Python. So what we're going to do is show 5 steps to get Horovod working with your existing training script. You initialize the library, pin a GPU to each worker, wrap the optimizer, synchronize states, checkpoint on the first worker. All right, that's the end of the talk. Hope everyone enjoyed that. Just kidding. Okay, so initialize the library. Import horovod.tensorflow as HVD, so you'll have a separate import statement depending on what framework you're using. In this case, we're using TensorFlow. And then you call horovod.init. So what that does is it does some basic bookkeeping, sets up communication between workers, allocates buffers, that sort of thing. Next step is we pin each task to a GPU. So this is actually something that tends to come up as an issue on GitHub, I think, every day, as people get a little bit confused about this. So we have this diagram here to hopefully make this easier to explain. But essentially, you want to ensure that every worker is using basically just one of your GPU resources. So what you'll typically do is spin up one process per GPU that you have in your environment. And then you want to avoid that sort of contention of having them all use like, a random GPU. So we do this pinning process where we say, okay, my ID relative to what machine I'm on is, let's say, 1, and I have 2 GPUs. I want to use GPU 1, and then, process 0 on this machine will use GPU 0. And so essentially that statement there that says the visible device list equals the local rank of this machine just achieves that effect of saying, use whatever GPU in terms of its identifier maps to my process. Next, we want to do the wrapping of the optimizer. So this is where Horovod's higher level Python API does a bit of magic for you. So we have this distributed optimizer as a convenience class that will handle pretty much all of the under the hood Allreduce calls. So it will automatically call Allreduce for you as the gradients have been computed and before the backwards pass begins. Optionally, we also suggest that you scale the learning rate. This was something that was suggested by Facebook in their paper, Accurate Large Mini-Batch SGD Training with ImageNet in under an hour. So effectively what you do there is we just scale it by horovod.size. So the more workers you have, the more the learning rate is going to scale. And then typically what you do in practice is you would also scale the learning rate over time. So in that formula there, n is the current step that you're on. And you would usually use some smooth warm up for the first number of epochs. And if you're using the Keras API, we actually provide a nice callback function for you there called learning rate warm up callback that will do this for you. Fourth step is going to be to synchronize state across the workers. So we have this call. We have this concept of hooks that you call. So broadcast global variables hook. So a broadcast operation in MPI land just means from one worker, send some information to all the others. And passing in 0 there just essentially says use parameter 0 or rank 0. So like the first worker in the chain. And so what this will do is it will ensure that all the workers end up starting with the same weights. Otherwise, the average gradient won't necessarily point towards the minimum. So, you know, in a deep learning application, typically your weights are going to be initialized randomly, right? And so what this will do is just ensure a consistent starting point for all the workers, so that in the case of, you know, what we see in the graph there, in the diagram there, is that if you didn't do this step, where red is the average gradients between the two workers, you could potentially end up exploring some completely different part of the space, right? And then finally, checkpoint on the first worker, kind of an underwhelming way to end the steps because it's very straightforward, I think, but essentially the model should be or will be consistent across all the workers after the synchronization is done. So there's no need to checkpoint it on every single one of the workers. We just restrict the checkpointing to be one of the workers. And then you see there that we also use this within a monitor training session. Monitor training session is nice. It provides some nice convenience functions, but one important thing to note about Horovod is that it's not coupled to any specific way of running TensorFlow. As we'll see later, you don't have to use a monitor training session. So to work through a few examples now, just to show you how all this fits together. Basic TensorFlow example, in bold are the parts that kind of apply specifically to Horovod. So we go ahead and import Horovod. Initialize is typically the first thing that we do. We go ahead and configure the config proto for our session, where we set the visible device list. You build your model. You do the wrapping of the optimizer, set up the broadcast global variables hooks, and then start your session and do your training. And this also works for the estimator API that TensorFlow provides. So estimators, for those that don't know, mostly handle even additional abstraction of doing things like abstracting away the validation, for example. And as you can see, the code is exactly the same, with the exception that at the very end, instead of using a monitor training session, you're going to use an estimator instead. Yeah, oh, sorry, no, the checkpointing is, yes, still, yeah, forgot to bold it, but it says there only checkpoint on rank 0, and then for the model dir, you pass in the checkpoint dir, and if it's none, it won't checkpoint. Good question. Okay, so Keras. Keras, pretty much exactly the same again. For this example, we did not list the checkpointer, but yeah, pretty much the same across the board. You build your model, you call model.fit. But one nice thing about the Keras API is that we have a lot of these callbacks available to you that you can take advantage of that do some of the boilerplate stuff, or in some cases, some of the more advanced stuff for you. And then finally, PyTorch. PyTorch, one thing that I think is worth noting about Horovod is that even in PyTorch, which is a completely orthogonal framework from TensorFlow, you still end up with Horovod code that looks pretty much identical. The one exception there is that instead of having a TensorFlow config proto, you are setting the CUDA device. But other than that, it's pretty much the same. You'll notice that we also pass in to the optimizer information about the model's parameters, because PyTorch encapsulates that information within the model as opposed to having it be kind of more of a global variable. And then finally, with regards to getting this up and running, how do you actually start the process? So it's just slightly more complicated than running Python on your training script. We use MPI to run Horovod. So for example, if you want to run on a 4 GPU machine, you would specify NP for num processes equal to 4, and then you would say -h for what hosts. For your local host, your local machine, :4 processes. And then you have some generic interfaces, and then your training script, and whatever environment variables you want to pass. So the interfaces might look a little bit arcane at first blush, but that's pretty standard stuff that's specific to your cluster and your networking environment, things like that. And the nice thing about this is that once you figure out what those interfaces need to be, and usually they're just these, then you don't need to consider that again in the future. You just write a wrapper script or something, which is what we do. And then you never have to look at them again. You just say mpi run.sh or whatever your actual training script. And then if you want to scale this out to multiple machines, you still specify how many total processes you want to use, in this case 16. And then you just pass in a comma separated list of the hosts that you actually want to run the training on. But if that's too much work, now there's an even better option for some cases, running Horovod on Spark. So I think running on Spark is a particularly appealing thing because it allows you to kind of couple your data pipelines with your actual training process and do it all within a nice environment like Jupyter Notebook here. So like many of our users are coming from this world of Spark, like I mentioned before, and this allows us to further separate things and leverage these existing Spark workers to go ahead and do the training for you. So what this does is hides the complexity of launching MPI run from the user, allows them to use the existing tools that they like to use, like IPython. And also we, as I guess like a quick plug for the Petastorm talk that's coming up soon, so they didn't pay me, I promise. You can save your data frame to Parquet and then use Petastorm for data ingestion, which will go ahead and take care of the random shuffling, fault tolerance, et cetera, which is something that currently RDDs are not optimized for out of the box. So Petastorm will go ahead and do that on your behalf. So Petastorm being a library specifically for feeding data to deep learning systems. Okay, so now you know how to run Horovod. Let's talk a little bit about some of the additional choices you can make when using Horovod if you want to configure it a bit more to the specifics of your use case. So data set. One option to feeding data to Horovod is data partitioning. So you shuffle the data, you split it up in such a way that each worker gets some subset of the data, and then you repeat this process at the end of each epoch. So this works very nicely. It allows you to end up in a situation where you know that all the examples are going to get used, that they're not going to be repeated in the training within a single epoch. But the one sort of caveat to watch out for, which we note in the yellow box there, is that, and this is the source of some user-facing issues that come up, is you need to ensure that the data is evenly split amongst all the workers. Otherwise, you can imagine that you have this problem where one of the workers finishes all its data and then another worker is still processing. It says, I'll reduce these tensors, and then nothing ever happens, and that ends up in a deadlock situation. But if you want to just nicely avoid that problem entirely, you can also use random sampling. So random sampling, you shuffle the data set, but instead you just have each worker say, just give me a random piece of the data set. And it turns out that in practice, this ends up working pretty similarly. So in practice, both approaches we found typically yield the same results. With the data partitioning, you prevent the issue of records being potentially trained more than once, but it causes issues if the batch sizes are not homogeneous. Whereas with random sampling, some of the records may be read multiple times in each epoch, others may not be read at all, but you know that you're not going to run into that potential deadlock issue. And validation can also be distributed, but an important caveat there, need to make sure to average the validation results from all the workers if the learning rate schedules depend on that validation result. And again, in Keras, we provide a nice metric average callback for you that will do that for you. So now let's talk about some of the things that we've been working on with Horovod recently. So gradient compression has been a big one. This is something that we've gotten a lot of contributions from on GitHub in the open source. So gradient compression, what you do is we have a compression API now that we expose, where as part of constructing the optimizer, you pass in what kind of compression you want to use. Currently FP16, half precision floats is what we support, but there's more coming. And the value proposition here, of course, is that you want to reduce the arithmetic bandwidth that you're utilizing of the GPU, and also reduce the amount of the amount of data sent over the network. So to talk quickly about FP16 specifically, FP16 half precision floats have much less precision in the mantissa than 32-bit floats. But it turns out in most production use cases for deep learning, you really care more about the magnitude and the direction of the gradients as opposed to necessarily those little bits of precision. And what we've seen from some of our users that have tried it out is that they've seen upwards of 17% improvement in the time to convergence for their models, and that the model performance itself has not seen any noticeable at all degradation in quality from the examples or from the trials that we've run. Another recent addition to Horovod has been hierarchical Allreduce. So with this, you specify an environment variable to Horovod that it will pick up in the lower level. And this was a contribution to from Amazon. And what it does is it first Allreduces locally and then performs Allreduce across nodes in parallel, where every node is going to be responsible for a different chunk of the buffer to be Allreduced. And it tends to work best in very large environments where you have many hosts, many GPUs. And specifically, one caveat is you need to make sure that the nodes are homogeneous in terms of same number of GPUs per node in order to get the most benefits out of it. But in some situations, we've seen anywhere from a 35 to 40% improvement in the time to train on large clusters, which is a really huge improvement. And since hierarchical Allreduce is a little bit of an interesting, I think a very interesting kind of approach, I'm going to quickly walk through an example of what it would look like. So you imagine before Allreduce, you have these 4 separate buffers that you want to make into the same buffer, right? So the first thing you're going to do is what's called a reduce scatter. So reduce scatter is equivalent in terms of the effect to an Allreduce locally followed by a scatter. So in the case of host 0 there, we're going to make the 2 buffers the same, and then we're going to split the buffer evenly between the different workers. Next, we're going to do a remote Allreduce in parallel. So here, different processes of the same local rank are going to do an Allreduce within themselves on that subset of the buffer that they're each responsible for. And then finally, a gather occurs locally that makes the buffers consistent across all the workers. So the net effect here is that you're able to kind of divide and conquer a little bit within the process of doing the Allreduce to speed things up. And tensor fusion is a feature that we've had in Horovod for some time now, from day one. It's a batching process where you batch tensors together, and the threshold that you set defines like the amount of batching that you're going to do in bytes, and the cycle time tells you how long you're going to wait between producing a new batch to send for Allreduce in milliseconds. But recently we've been doing a little bit of work in trying to make these settings a little bit more configurable, or a little bit more customized to your model and your environment. So this here is a visualization of, it's a little bit complicated. So it's a 3-dimensional visualization, but kind of split up a little bit. So what we have on the x-axis is the cycle time in milliseconds that you set for Horovod. And then we see that we've stratified this in terms of different fusion buffer thresholds. So 0 megabytes meaning no fusion buffer, 1, 2, all the way up to 64 megabyte thresholds. And then the blue line, there's going to be using regular or what we call flat Allreduce. And then the green line is going to be the performance in terms of images per second of hierarchical Allreduce. And what you see is that as a function of the cycle time and the fusion buffer threshold, hierarchical Allreduce for this particular model in this environment did outperform the normal Allreduce, but it required finding those right values of the fusion buffer and the cycle time. It didn't just come automatically. In fact, our defaults currently are 64 megabytes for the fusion buffer size, in which case normal Allreduce would have outperformed in this instance. So how do you go about actually picking these values? Well, there's really no formula that we know of right now. It's a very kind of ad hoc trial and error process. But what we've been working on recently is what we're calling an auto-tuning system that leverages Bayesian optimization to try picking new values based on its previous observations of how the previous values performed. And then what it will do is converge to what it determines to be the most optimal values on your behalf without you having to do any setting yourself. And then once it finds the right values, it'll go ahead and run with it, and you'll get the best training that you can. So to wrap up, some results of how Horovod has worked out for us. So Horovod is now the only way that our teams internally do distributed training at Uber. We've managed to train both CNNs and LSTMs in hours instead of days or weeks, which has been a big boon for a lot of teams here at Uber that have very large models with lots of data. And now Horovod is also being widely used by various companies. We've been working a lot with NVIDIA, Amazon, Alibaba, and research labs, including Oak Ridge. And Horovod is also now included in various deep learning distributions, AWS deep learning, GCP as well, Azure, NVIDIA GPU Cloud, IBM Databricks, and IBM Watson Studio. So open sourcing Horovod, to make a long story short, has been a great thing for Uber and for Horovod. We've gotten so much great feedback from the community in terms of contributions and also just engagement in terms of adoption. So it's been really great to see, and we're really looking forward to seeing what continues to come down the pipeline. So with that, thank you very much for coming. And if there are any questions, I think we probably have some time.